Okay, so in 2.5, we're going to finish chapter 2 talking about the derivatives of trig functions. We'll prove a couple, and the other proofs will be left for you to do in your homework. So our goal in 2.5 is to see how trig functions are used in harmonic motion, to learn what the derivatives of sine and cosine are, to develop the derivatives of tangent, cotangent, secant, and cosecant, and then to work with tangent and normal lines. Things that change periodically, that means they follow a repeated pattern of change. They change positively, that they change negatively, and that cycle repeats itself. Those are called periodic functions or harmonic functions, sometimes even called sinusoidal if that's the model that they follow. So what we want to start with is the definition of the derivative of sine. So sine's derivative is defined as cosine, and then we want to go through how do we prove that that is true. So the proof of that comes from using Newton's definition. And so we'll work through that together, and then you'll do the other one on your own. So the derivative of sine of x. So by definition, that would be the limit as h approaches 0 of the sine of the quantity x plus h minus the sine of just x all over h. So Newton's definition, and then we expand that so that we can simplify and prove that cosine is the result. So we're going to use the sign of a sum, which is the expression sine, cosine, and then added to cosine sine. So this would be the sine of x, the cosine of h, plus the cosine of x and the sine of h. And that comes from the expression that sine of x plus h minus sine of x all over h. So we're just proving it now. You don't have to reprove it every single time. Once we've proven it, you can take the definition and just run with it. The only thing you would have to prove is to prove the reverse, to prove the cosine derivative. So we're going to factor this equation. And what we notice is that the only thing that this numerator has in common is a sine of x here and a sine of x at the very beginning. So we have a sine of x in both of those expressions. So if we reorder this equation, we'll have the sine of x times the cosine of h, and then minus the sine of x, and those two things are in common, over h. And then we add to that the cosine of x and the sine of h, and they are over their own common denominator of h. And I'm going to put big parentheses around both of those. I'm going to have to slide over a little bit and give myself a little more space. So then I factor. Sine of x is common in the first term. So I'll have the limit as h approaches 0. I'll have the sine of x factored out of the cosine of h minus 1. And that's over h. And then plus a separate limit as h approaches 0 of the other part that was left. So the cosine of x times the sine of h over h. Now the variable here is not x. The variable is h. H is what is approaching 0 in the limit. And because the variable is h and not x, I can take this sine and move it to the front. And I can take this cosine and I can move it to the front. So I'll have the sine of x times the limit as h approaches 0 of the quantity cosine of h minus 1 over h plus cosine of x in front of the limit of sine of h over h. Now both of these limits have a particular defined value. We've learned this limit, the second limit, the sine of h over h as h approaches 0, that has a limit value of 1. We proved that in chapter 1. Cosine of h minus 1 over h, that has a limit value of 0. We haven't proven that yet. You need L'Hopital's rule to prove that, which we technically haven't learned yet. So you'll just have to believe me that this is 0. And so since that limit value is 0, you could also prove it with the squeeze theorem, actually. You know what? You could prove it with the squeeze theorem, which we do know. So we can be rest assured that that value is 0. And so 0 is going to wipe out the sine of x, and 1 will multiply by cosine of x. And so we get cosine of x as our answer. And so we have now proven that the derivative of sine of x is cos x. The reason I showed you that is so that you can do the cosine version of this as part of your homework, but you don't have to reprove sine every single time. You can now take it as a definition. So the derivative of cosine is negative sine, and then this will be to be proved in your homework. So let's practice taking the derivative of something using a combination of the quotient rule and the trig rules. So we take the derivative, d dx, of the quantity sine of x over cosine x minus 2, and we're going to use the quotient rule to do that. So cosine of x minus 2 times the derivative of sine of x, which is cosine of x, minus sine of x times the derivative of the cosine of x minus 2, which is negative sine of x, all over the quantity cosine of x minus 2 quantity squared. So we clean that up, and we'll end up with cosine squared x minus 2 cos x plus sine squared x over the quantity cos x minus 2 squared. And hopefully you notice that you've got a cosine squared plus a sine squared in the numerator. So that's 1 minus 2 cos x over cosine of x minus 2 quantity squared. And that can't be simplified anymore. That would be as far as you'd want to take that. Any questions so far? It's coming back, right? You're remembering? We can also find tangent lines using the derivative, the trig derivatives. You need a point and you need a slope. And so our point is going to be 1 comma 1 times the cosine of 1, which is 1 cos 1. Okay, this is not cos pi, this is cos 1. It is not, don't find the decimal, please. Just leave it in its exact form because 1 radian doesn't have a very nice cosine value. So just leave it as the cosine of 1. The slope would be the derivative, using the product rule this time. So that would be A times B prime plus B times A prime. And then finding that value at 1, so M would equal 1 times the negative sign of 1 plus the cosine of 1. So we're looking at cos 1 minus sine 1. Again, don't turn that into a decimal. Just please leave it in its exact form. So then your tangent line would be y minus cos 1. The slope is cos 1 minus sine 1, and then x minus 1. And you don't have to simplify that. You can leave it in its point slope form. Some of you like to make your ones look like this. That just takes me too long to do that. Okay. So here is a picture of that same function and what its tangent line would look like if you graphed it. So that tangent line skims across at the point 1 comma cos 1, and this is the decimal equivalent of what that would look like as you have your tangent line coming down and skimming off the top of the curve. It also intersects in other places, but it's tangent only at 1 comma cos 1. All right, these are the other derivatives. Each of them can be proven not with limit definition. The only time you need limit definition is for sine and cosine. Once you've proven sine and cosine, you can use those to prove the rest of all of these. So I'm going to demonstrate how to do tangent for you, and then you'll use that as your model to prove the others as part of your homework. So the derivative, d dx, the derivative of tangent is proven by actually taking the derivative of sine over cosine. So first you replace tangent with its identity, and you'll do that with all of these proofs. And then you use the quotient rule to simplify. So the derivative of the quotient sine over cosine would be the cosine of x times the cosine of x. So that's b times the derivative of a minus the sine of x times the negative sine of x, all over the denominator of cosine x quantity squared. So my numerator becomes cosine squared plus sine squared over the denominator quantity cosine squared x, which is the identity 1 over the cosine of x. And that quantity is squared, which means the reciprocal is going to be secant squared of x. And so now you've proven the derivative of tangent by using an identity followed by the quotient rule. And so the other proofs, the other 3, are going to be done in your homework as well. Once you've proven them, you don't have to reprove them. You can just use the definition. So cotangent is negative cosecant squared. Secant is a product of secant and tangent, and the derivative of cosecant is the product of negative cosecant cotangent. So just a reminder, if the trig function is one of the cosine, cotangent, cosecant, if it's any of those, its derivative will have a negative value. And so derivative cosine is negative sine, derivative cotangent, negative cosecant, and then cosecant is negative cosecant cotangent. So just a few quick examples. You can use now the definitions of the trig values to find multiple derivatives. I apologize, this is a typo right here. That's not y to the n, that's y double prime. Okay, so find the second derivative. So the first derivative of cosine tangent would be negative sine of x plus secant squared. To find the derivative, which also could be written negative sine of x plus quantity secant x with the square on the outside. Then you find the second derivative. The derivative of negative sine is negative cosine. The derivative of secant squared requires you to pull the power down to the front. So that would be 2 times the secant of x to the first. And it technically also requires you to remember a rule that we haven't reviewed yet, but does apply here, which is the chain rule. And so to take the derivative of what's inside the function, inside the parentheses also, which would be another secant and tangent. So a cleaner version of that would be the negative cosine of x plus 2 times secant squared tan x. And the last two slides, connect the last two lessons. It connects the idea of velocity and acceleration, which we started with, and then connects it to trigonometry. So when you combine velocity and acceleration with something that is trigonometric or periodic, the motion is repetitive. Okay, it's something that happens over and over. So a common example would be something bobbing up and down on the end of a spring or something like that. That's called harmonic motion. And so if you're given the model for harmonic motion as 3 sine t, you can find the velocity and acceleration by taking simple derivatives. So the velocity from 3 sine t would be 3 cos t, and the acceleration is a simple, measured in meters per second. And then acceleration would be a simple derivative again, so negative 3 sine t, now measured in meters per second squared.